Okay, let's dive right in and uncover how the invisible, non-stop movement of tiny particles dictates the physical properties of literally everything around us. Have you ever just stopped and wondered why an ice cube holds its shape while water just slips right through your fingers and steam seemingly vanishes into thin air? Well, the answer to that actually lies in a hidden universe, one that's entirely invisible to the naked eye. So today, we're exploring the kinetic particle model of matter. Here is a roadmap for today's explainer. We'll start with the three states of matter. Then, we'll break down the kinetic particle model itself. After that, we'll look at the ultimate proof, Brownian motion. We'll drop things down to temperature and absolute zero, and finally wrap up with gases and pressure. Let's get to it. Starting off with section 1, the three states, solid, liquid, and gas. To build our understanding, we really need to start with the familiar baseline of how matter exists in our everyday world. We can easily observe matter in three states, right? Think about water. You've got ice cubes sitting rigidly in a glass. You've got colored liquid that perfectly takes on the exact shape of whatever wacky glass flask you pour it into. And of course, you have water boiled in a kettle that turns into an invisible gas, which then quickly condenses back into visible droplets the second it hits the cooler air. Heat a solid and it melts into a liquid, heat that liquid to its boiling point, and boom, it becomes a gas. These are the fundamental changes of state that we experience every single day. Now, this perfectly illustrates how we categorize these three states. Solids, they have a rigid, fixed shape and a fixed volume. I mean, you can't just squash an ice cube into a smaller space. Liquids, on the other hand, aren't rigid. They take the shape of whatever container you pour them into, but, and this is key, their volume stays exactly the same. You know, there's actually a famous psychology experiment where a young child thinks a taller, narrower glass holds more liquid than a wider, shorter one. The child just hasn't realized yet that liquid has a fixed volume, totally regardless of its shape. And finally, we have gases. Gases are the rule breakers. No fixed shape, no fixed volume. They will expand to completely fill whatever container they're put in, and unlike solids and liquids, they can easily be squashed or compressed. Moving on to section 2, the kinetic particle model, where we take a microscopic view. Now, what's really interesting here is how we explain those physical differences we just talked about by zooming way, way in. The word kinetic simply means related to movement. So this entire scientific model is based on the idea that all matter is made up of tiny, constantly moving, identical spherical particles. We know these today as atoms, molecules, or ions. Now, scientists use models to explain things we can't see directly. And sure, drawing every atom as a perfect tiny sphere is a bit of a simplification, but it gives us an incredibly powerful framework. It helps us answer questions like, why exactly does it take time to melt a solid? Or how is it possible that we can smell perfume from literally all the way across a room? Take a look at how these particles are arranged. It's like a giant puzzle. In a solid, the particles are packed super closely together in a regular, tight pattern. There are really strong attractive forces, bonds, holding them in place. Because they're packed so tightly, they can't actually move from place to place. They just vibrate right there in their fixed positions. But as we add heat, we're adding kinetic energy. The solid melts into a liquid. Now, the particles are slightly further apart. Those bonds are a bit weaker, and the arrangement is random. They're still vibrating for sure, but now they can slide past one another. And finally, the gas state. Here, the particles are widely separated. We're talking about 10 times their diameter apart. In the air around us right now, they move freely, randomly, just bouncing off one another. To put that into perspective, in the air at room temperature, these gas particles are zipping around at a staggering average speed of 500 meters per second. Which brings us to section 3, evidence, specifically Brownian motion, which is basically our smoking gun. So you might be wondering at this point, if atoms and molecules are far too small to see, how on earth do we actually know they're moving? It's a really great question. I mean, air molecules have an average diameter of about 4 times 10 to the power of negative 10 meters. They are utterly impossible to see, even if you had the most powerful laboratory microscope in the world. So if we can't see them, how do we know they are zooming around at hundreds of meters a second? Well, the answer takes us all the way back to 1827. A scientist named Albert Brown was using a microscope to study tiny pollen grains suspended in water. He noticed these grains were constantly jiggling around in these random, erratic paths. At first, he actually thought the pollen might be alive. But then he repeated the exact same experiment with inanimate dust and, guess what? He saw the exact same jiggling motion. Today, we can recreate this phenomenon, which we now call Brownian motion, in a modern lab using something called a smoke cell. Check out this large yellowish sphere representing a smoke particle. Because the smoke particle is made up of many molecules, it's roughly 250 times larger than the individual air molecules around it. That makes it just large enough to show up as a little speck of light under a microscope. And as you watch it, it follows this incredibly random, jagged, constantly changing path. Why is it doing that? Because those incredibly fast-moving, entirely invisible air molecules are constantly crashing into it from all sides. The air molecules might be tiny, but because they are moving so incredibly fast, they pack enough kinetic energy to physically knock that massive smoke particle off course. It is the absolute perfect microscopic smoking gun, proving that particles are, in fact, in constant motion. Let's move on to Section 4, Temperature and Absolute Zero. This is all about energy and motion. Now, our everyday Celsius scale was cleverly devised by Anders Celsius by basically calibrating thermometers to two fixed points, the melting point of pure ice at 0 degrees and the boiling point of pure water at 100 degrees. But scientifically speaking, temperature is actually a direct measure of the average kinetic energy of the individual particles in a substance. If the particles are moving faster, the temperature is higher. It's that simple. And that brings us to the Kelvin scale, or the absolute temperature scale. Unlike Celsius, the Kelvin scale doesn't start at the freezing point of water. It starts at the absolute lowest energy state mathematically possible. So the absolutely crucial point here is that if a substance cools down, its particles are losing kinetic energy, which means they slow down. Logic dictates there just has to be a theoretical lower limit to how cold anything can get. If the particles lose all of their kinetic energy and completely 100% stop moving, it is physically impossible for the substance to cool down any further. This rock bottom, ultimate limit is called absolute zero, and it occurs at exactly negative 273 degrees Celsius, or on the Kelvin scale, simply 0 Kelvin. Finally, let's dive into Section 5, gases and pressure, and specifically Boyle's law. Let's see what happens when we trap these energetic gas particles in a container. Think about the last time you pumped air into a bicycle tire. Why does it get so hard? Well, the kinetic model tells us that gas pressure is simply caused by millions of tiny particles constantly colliding with the inner walls of whatever container they're in. They hit the wall, change their momentum, and exert a continuous force over the area of that wall. So, if we squash a gas into a smaller container, meaning we decrease its volume, the total number of molecules stays exactly the same. But because the space is now smaller, those particles don't have to travel nearly as far between collisions. Therefore, they hit the walls much more frequently, and more hits per second means more force on the walls, which naturally means the pressure increases. Way back in 1662, a scientist named Robert Boyle investigated this exact relationship, and he discovered something amazing. If you keep the temperature constant, the volume of a fixed mass of gas is inversely proportional to its pressure, meaning if you have the volume, you double the pressure. Mathematically, we express this as P times V equals a constant. This is Boyle's law. It's a beautifully simple yet profound equation that lets us predict exactly how a gas is going to behave when compressed. It explains everything from how you breathe using your diaphragm to how a trumpet produces a loud sound. And that wraps up our journey, going from the everyday macroscopic objects we can hold, all the way down to the microscopic forces that shape them. We've explored the hidden kinetic world today, and we've seen how the constant, chaotic dance of atoms and molecules determines whether a substance is a solid, a liquid, or a gas. So, my challenge to you is this. Look at the macroscopic world around you today and try to visualize those invisible particles at play. Next time you smell your morning coffee, think of those gas particles aggressively diffusing across the room. It really changes how you see the world. Until next time, keep questioning the world around you, especially the parts you can't see.